All right, good morning. So let's get started. Can one of you please confirm that I'm audible? Okay, great. Okay, so in the at least in the course so far, we've mainly been discussing variable length compression algorithms with zero error. We saw a number of compression algorithms, all achieving an expected length or an average rate close to the entropy or close to the entropy rate. Uh, we first saw the Crafts inequality, which gave us uh, some necessary and sufficient conditions for prefix-free codes, and then using that we got a lower bound saying that if we want to compress any source using a prefix-free code, then the expected length must necessarily be greater than the entropy. We then saw a number of practical compression algorithms, the Shannon code, the Huffman code, the Shannon-Fano-Elias code, and then we extended these to get the arithmetic code. All of these were codes which assume that the source is given or the true distribution is given to the compressor and the decompressor. If the true distribution is not given and you use a proxy Q instead of the true distribution P, then we saw that there is a loss. Then in the last couple of classes, I discussed the Lempel-Ziv algorithms, which are universal compression algorithms. They work irrespective of what the true distribution is. They will always get you close to the entropy rate for asymptotically large block size. Right? And in a couple of lecture videos, I also shared some recorded lectures which discussed fixed length compression with vanishing error. This was also part of your homework one. So it turns out that the fundamental limit of compression, irrespective of whether you're using a variable length compressor or a fixed length compressor, asymptotically, the best that you can hope for is still equal to the entropy. Right? So the minimum rate of compression, as long as you want either vanishing error or zero error, the minimum rate is always equal to h of xn by n. So as long as it's a stationary and ergodic source, this is the best that you can possibly achieve uh, using the best possible compression scheme. So for an IID sequence,
Sir, you are not audible.
am I audible?
Yes, sir.
Uh, okay, so I'm not sure at what point you
Uh,
lost me.
so you started saying about IID.
Okay, so for IID sources, the best possible rate that we can achieve if we want either zero error or a vanishing probability of error, the best possible rate is equal to the entropy h of x. Right? But in many scenarios, uh, we want to do even better. At times, vanishing error, reconstructing the source exactly is not particularly important. As long as you have a close enough representation of the source, it's fine. So So zero error is typically what you require when you're dealing with, say, text files or images.
So you're not audible again.
Yeah, sorry again. Am I audible now?
Yes, sir.
All right. So as I was saying, variable length compression is with zero errors typically used when you have data like text files or yeah, so large databases and so on. So these are cases where even a single bit of error is cannot be tolerated. Now, fixed length compression with vanishing error is something that could be used when you're transmitting files across a noisy channel. Right? So in these scenarios, the channel is anyway going to introduce some errors. So there's a small error probability that is induced by the channel, and an additional tiny bit of error induced by the compression algorithm is still okay. So in these scenarios, one can go for fixed length compression. Uh, but but again, this really depends on the application. Typically, the most commonly used compression algorithms are variable length compression algorithms with zero error. Now, there are many other applications where it's okay even if the number of errors is a bit more. So when we have, say, images, or if we have, say, videos or audios, it's okay even if it's okay if we don't, if we are not able to reconstruct the true source exactly. A small amount of distortion is perfectly okay. And in certain cases we have to do lossy compression when, for example, the alphabet is infinite. So so both in variable length compression and fixed length compression with zero or vanishing probability of error, we always assume that the alphabet size is finite and typically not too large. So in a typical scenario, the alphabet size would be like say 256 or maybe 1,000 or so, but not more than that. Think of like ASCII text files where each symbol is typically just an ASCII character. But when we're dealing with, say, audio files or images, or if we are, say, we are taking samples using a sensor, then the source could be real valued. So the alphabet X could be R, or sometimes a set of complex numbers, or more generally, RK or CK, etc. Right? So when the source itself is over a continuous alphabet, it is impossible to represent this exactly using a finite number of bits. So the only thing that you can hope for is just a coarse representation of the source. And so you have to quantize the source if you want to store it or transmit it using a finite number of bits. So that is where we come to when we talk about lossy compression. But lossy compression, or quantization as it's also called, is not just used for in the case where the alphabet is infinite or where the alphabet is very large. It can also be used when the alphabet size is small. So when the alphabet size is small and you're allowed to tolerate a small amount of distortion, it turns out that you can do lossy compression. You can compress the source at a rate much lower than the entropy, but of course the price that you pay is the distortion. All right. So in the next couple of classes, I'll just walk you through the general theory of lossy compression. What is the best rate that we can hope for when we try to quantize a particular source? And I won't talk too much about the algorithms involved, although I will spend a little bit of time talking about one or two of those. Uh, but since the time is limited, I'll only discuss what is the best possible rate that we can achieve for lossy compression for a given distortion, and see how we can derive this. All right. So, but before we proceed to lossy compression, are there any questions regarding the topics that we've covered so far? Yes, any questions?
Sure, in case of LG 77 and 78 compression, in order to
Yes.
encode integers, why don't we just use a mapping from those integers and that space to general numbers and then use Huffman coding or Shannon
Uh,
coding on that?
Sorry, I didn't. So you're saying that you just convert the integers into. Okay, so how do you propose to do it? You have an integer, so let's
Yeah,
say
we have
20,
list of all the phrases,
correct?
and we know how many times each one is occurring.
How many times each what is occurring?
Each integer, like the first
Okay,
entry of
okay,
each phrase,
sure,
uh,
sure.
we get the probability distribution of the first
Of the
entry.
integers,
Yeah, and
yep.
from that we can use Huffman coding or something else, right? Because that in a way seems far better than using log n plus 2 log of log n plus 1, right?
So again, it depends because in general this might not be optimal. And the reason why it might not be optimal is that after all, you need to store you need to store the distribution of the integers, right? And
Correct.
and typically the alphabet size is very large. So let us say that, okay, so you have a sequence. So you have a sequence of length n, right? And what would the alphabet size look like? The alphabet size could be as large as log n, right? Because the integer could be as large as n, right?
Yes.
Right. So, sorry, the alphabet size itself could be as large as n, right? So
And
it takes log n bits, but the alphabet size could be as large as n, equal to the number of symbols itself, right?
Yes.
So in these scenarios, you may not have a good estimate of the actual distribution, right? And even if you try to do something like Huffman coding, you would not really achieve too much gains, because for many sources, the number of times each integer repeats would not be too large, because really small integers, these occur not too many times, because short phrases don't occur very often. It is the longer phrases which occur more often, and that's typically the case if the text is well compressible, right?
Yes.
So overall, you would still require roughly log n bits to represent each integer. You could potentially get some gains, but that's an additional overhead, because you have to first design the Huffman code, right? And then both the encoder and the decoder have to design the Huffman code, and you need to store the probability distribution as a header, which is something additional in terms of the text, or in terms of the file size. So the gains aren't that much to make it sort of attractive to use in practice. It's far simpler to just use this generic algorithm, which you can just very easily encode and decode,
Okay. Thank you.
right? But agreed. So in certain applications, it might be more useful, but generally the distribution of the integers will be is not skewed towards the small integers. It is somewhere in between the large integers and something in between, right? Because longer phrases or moderately long phrases occur more often than the small phrases. Okay, so any other questions? Yeah, but maybe continuing along those lines, uh, while it is not, yeah, while encoding the integers using say Huffman codes, or some of these, or Shannon codes, or so on, is not very useful. One thing that is done is that when you want to encode the characters, for example, in LZ78, each phrase is encoded as an integer and a character, right? And this character occurs in every phrase, right? The last character of the phrase. So so to encode that, people typically do use Huffman codes or other compression algorithms that we've seen, and I think that is called the Lempel-Ziv-Welch algorithm. It's a slight modification. It's basically just uh, a very minor modification, but that is used in practice. So to encode the character, you don't encode it using a fixed number of bits. You use something like a Huffman code to encode it. But in practice, when the Lempel-Ziv algorithms are used, there are a lot more things. So a compressor like zip, or even JPEG or something for that matter, or similar algorithms for that matter, they don't use Lempel-Ziv as it is. The way you store the integers, the way you store these characters, the way you construct or the way you compute the phrases, all of these are not done in the form I described to you. There are several engineering optimizations that are done in order to improve the compression speed, the decompression speed, or improve the file size. So depending on the application, you make minor modifications. In certain applications, the compression speed is more important than the compression length itself. So it's okay to tolerate a small extra compression length is fine, but then you want to be able to compress it as fast as possible, or you want to be able to decompress it as fast as possible. So so depending on the application, you make several changes, right? And I guess so a couple of you will be talking about some of these algorithms as part of your final paper project presentation. So for example, so different applications could be like when you're storing something on disk, say using zip or 7-zip, the compression and decompression speeds are not too much of a criteria. The file size is the most important thing, right? And so zip is not optimized for compression and decompression speeds. It's optimized for having for giving the smallest file size for text files. On the other hand, uh, so so for example, if you used Linux before, uh, you download, so whenever you're trying to update certain packages or you're trying to download software, these files are compressed and sent to you, right, over the network. So these files are typically compressed and stored in a central server. But then when they come to you, they get decompressed, and then you run these to install the packages that you're interested in. So in these scenarios where you're storing a file on the server and a large number of people are downloading it and installing them, the compression speed is not so much of an issue because it's being compressed and stored at once. But then a large number of people are going to download and decompress. So in this sort of application, the compression length is important because you want to save bandwidth. But at the same time, decompression speed is also important. You want to be able to decompress as fast as possible because you want to install. You don't want to take a really long time to install a particular package, and there could be a large number of packages, right? So whenever you're designing a compression algorithm, you need to take into account a large number of factors such as these, and it's not a symmetric problem. In certain applications, you can tolerate certain things, really, you can relax certain constraints, but then certain constraints are very important. The compression speed, the decompression speed, and the compression length. There's always a trade-off between these, and ultimately, depending on the application, you choose which one to minimize and which one it's okay to have uh, a little larger or smaller. Right? Any other questions? Okay. So yeah. All right. So let's talk about quantization. Right? So if you look at any communication system or any application where you deal with speech or images or video, it's impossible uh, to get an exact or to store or transmit an exact representation of the source. So for example, if you have a speech signal, it's a continuous time signal, which you can assume to be maybe band limited, but uh, in general it requires an infinite number of bits to represent faithfully. Right? So if you have a speech signal, then what do? You first sample the signal. So you convert this into a finite number of samples, right? But then each sample is basically a real number. So from a signal of length t, maybe you have a recording of, or you want to record a speech signal of duration t seconds, you convert it into n samples, right? Which is basically, you can think of this as a vector of length n. That's just a mathematical representation. So from f of t, you just get f of I going from 1 through n. Right? And you could use several sampling techniques. Right? It could be uniform sampling. The sampling need not be uniform, but that doesn't matter. So ultimately, what we have, or what we are interested in, is this object. It's going to be a vector of length n, right? And our goal is to represent this vector, the sampled vector of length n, using a finite number of bits. And we want to minimize the number of bits to represent this sample. Right? So this is sampling. Right? And from the sampled signal, we then quantize. Right? You quantize this to a stream of bits. K bits. So from n real numbers, you are obtaining k bits, and so and this is either stored or transmitted across a medium, and then this is, you do a reconstruction. Right, to get again so it's impossible to reconstruct exactly, but then you reconstruct it with some distortion, a small amount of distortion. And then from the sampled signal, you again reconstruct this to get another speech signal, which is going to be different from this, which is going to be, these two are going to be different, but hopefully they're as close to each other as possible, right? And so what we will be interested in are these blocks, right? The quantization and reconstruction from the quantized bits to another stream of real numbers. Okay, so what we are given is a sequence of n symbols. These could be n samples of a speech signal, or these could be say n pixels of an image. Our goal is to compress this or quantize this. This is called an encoder or a quantizer. To get k bits, it's a code word of length k bits. And then you decode this to get some xn hat. Right? And our goal is to ensure that, of course, now we can't really aim for zero error or a vanishingly small probability of error. So what we ask for is that some distortion, so I'll define a distortion metric. And our goal is to say that some distance or some distortion between the reconstruction and the original source is less than some quantity delta, right? Some n delta. And we'll try to make it small in an expected sense. All right. So typically when we're dealing with, say, images, the distortion metric that we're interested in is typically the mean squared error. Right. So we have n pixels. Okay, and then we quantize this, and then from the quantized bits, we reconstruct it to get x hat, and what we want to minimize is the expected value of the squared norm. So typically it's 1 over n. So it is 1 over n times summation I going from 1 through n of the expected value of xi minus xi hat squared. So this should be less than some quantity delta. So this is called the mean squared error distortion. And this arises in a number of applications, in particular uh, in quantization of images. When we're trying to quantize, say, speech signals, certain other metrics are used. Depending on the application, you could use more complicated distortion measures. But one of the most widely studied and widely used distortion metric is this mean squared error distortion. Right? But in general, there are a number of metrics that you could minimize. So more generally, the LP metric, which is say 1 over n I going from 1 through n of the expected value of xi minus xi hat raised to the p. Right, you could say that this has to be less than some delta. Right, this is one example of this is not exactly the LP metric, but let me call it. This is my notation. It's not standard notation, but let me call the P error to be summation I going from 1 through n of the expected value of xi minus xi hat, absolute value of xi minus xi hat raised to the P. So this should be less than delta. If P is equal to 2, then we get the mean squared error, but for different values of P, you get different distortion metrics. Another example is the Hamming error or the Hamming distortion. And this is basically 1 over n, or the fraction of locations in which the two symbols differ. So the number of i's such that xi is not equal to xi hat. So here in this particular example, these two sequences differ in two locations. So the Hamming distortion is typically is 1 over n times 2 divided by 6. It's 2 divided by 6, so it's 1/3. Right? So the distortion that you choose depends on the application. But for a given distortion metric, our goal is to minimize the number of bits that are required to represent the source. All right. So any questions so far? Any questions? Okay, so maybe let us start with the most simplest problem, right? So we're given a random variable x. Let's assume that the distribution of x is given to us. Our goal is to quantize this. So we'll assume that x distributed according to x has a probability density function fx, and our goal is to represent this using k bits. And then you reconstruct this to get an x hat. And we'll assume that even the decoder also knows fx, right? Right, so just taking a step back, Anuradha asks, is it possible to extend the Lempel-Ziv algorithm to images and videos? So Lempel-Ziv algorithms are also used for lossy compression, although you can't really say that they're optimal. Right? So the Lempel-Ziv algorithm is used as one component of certain lossy compression algorithms. You could, for example, one thing that you could think of is that you use a plain quantizer. Maybe you take, say, a speech signal, you quantize it into a fixed number of levels. You keep it fixed irrespective of what the speech signal is. So you get a sequence of symbols, and then you can use the Lempel-Ziv algorithm to compress this further. So that is done in practice for certain applications, but generally it is not optimal. It doesn't give you the best possible rate. But certainly, if you did not have any information about the source sequence itself, and you want a fast enough quantizer, or you want a fast enough lossy compression algorithm, then one of the first things people think of is to do scalar quantization. You say quantize each symbol using a fixed number of levels, and then you use a lossless compression algorithm to compress the resulting sequence.
Okay, so only it is good to use on 1D signals, not for 2D
Uh,
signals.
Sorry, your voice, there's a lot of distortion in your voice. So,
Is it like this kind of like algorithms only like good for 1D signals only, so not for 2D and 3D signals?
yes. So all of these are typically used for one-dimensional signals.
Okay, so even for images and videos also, like
Uh-huh.
just we try to represent those using pixels instead of bits. Like can't we
Correct.
extend on pixels?
Uh, what do you mean extend on pixels?
Just the pixel values we need to take like whatever the algorithm that we used earlier on text or on 1D like values, 1D signal samples. Here we try to apply the same algorithm on 2D values, like pixels.
Correct. So each pixel can be represented by a number, right? Assuming so, for example, if it's a grayscale image, just for simplicity, each pixel is basically a number between or a value between say 0 and 255. Uh, and so you have of course, now actually you do, as you mentioned, you do have a two-dimensional sequence. So basically you have you can represent it as a matrix of values,
Yes,
say
intensities.
1024 by 1024, right? So it's a matrix of intensities, and that is basically how so the JPEG algorithm, for example, would take a transformation of this. You convert this matrix. Yeah, you transform this using, say, the discrete cosine transform, and that will still give you another matrix, but then you convert it into a one-dimensional sequence, into a vector, and then you use some other compression algorithm to store this.
Yes, sir.
So again, since it's an image, there are better things that you can do, but it turns out that this is good enough. You can just take a transformation of this and then vectorize it and then use a lossless compression algorithm and then do the reverse to reconstruct the image.
Okay, sir. Okay, this is not possible. Using any like algorithm that we like apply on 1Ds up to 2Ds and 3Ds. Is it possible, sir? In case if we have a best algorithm to compress images and videos, and using those algorithms on 1D signals, reverse.
Uh, I'm not sure I completely understand your question. So is your question why you can use this on 2D signals or
No, so this
yes,
you said that this is like no, we have best other algorithms to like use in case of images and videos. Like
correct?
what I'm asking is,
Uh-huh.
what are the best algorithm that we use for images and videos? Can
Correct.
we use the same algorithm on 1D signals?
Not necessarily. So the ones that would work best for 1D signals are not the ones which work the best for 2D signals and vice versa.
Okay.
So they're not optimal. So for example, the best compression algorithm for a speech signal would be very different from the best compression algorithm that you would use for images, right? So these
So
are yeah.
as it is universal, so got this question.
Okay. So, but again, when I say universal, the Lempenziv algorithm would be universal for a one-dimensional, for lossless compression of a one-dimensional sequence, right? So even if you had, say, a two-dimensional sequence where you have a finite number of levels or over a small alphabet, the Lempenziv algorithm is not optimal,
Okay, sir.
right? Uh, so so one could potentially extend the Lempenziv algorithm to work on blocks of like 2D sequences instead of one-dimensional sequences, but certainly that would not be the traditional Lempenziv algorithm. So Lempenziv kind of algorithms are designed for one-dimensional signals like text or sequences of that sort.
Okay, sir.
So for example, if you had to deal with, suppose you want to store a large database, which is basically a table, right? So you have a number of rows and columns. If you want to store large matrices, then the Lempenziv algorithm is not optimal. People still use something like zip to compress it, but it is certainly not optimal. You have other compressors which can do better than this.
Okay, sir.
All right?
Okay. Thank you, sir.
Okay, so right. So let's look at the sort of simplest setup where we have a single random variable, one realization of a random variable. Let us say that x is just a single real number, and I want to quantize this into a finite number of bits, into say k levels. Right? So let's say that x can take any is some number. Right, x is some number which can take any value between plus infinity and minus infinity, and this associated with x is a probability density function. For simplicity, you could assume that this is either uniformly distributed over an interval, or you could assume that this is a Gaussian distribution. And given the distribution, your goal is to quantize this into a finite number of levels. Right? So the quantizer, let me just call it Q perhaps. The quantizer Q is basically going to be a map which takes X and quantizes it into some finite number of levels. So one example of a quantizer could look something like this. So it's going to be a k level. So any general quantizer is going to be a k level quantizer where each interval is mapped to a particular level. Right? So this interval is mapped to 0. This interval is mapped to this particular level, say 0.1, and this interval is mapped to another level, let's say 0.2. Similarly, this interval is mapped to minus 0.1. This is mapped to minus 0.2. This is mapped to minus 0.3, and so on. Right? So a quantizer is, you can think of it basically as something like a step function, right, which has a finite number of steps. Okay, but a quantizer in general could be something more complicated. Right? All you're fixing is the number of levels. So a k bit or a k bit quantizer would have 2 to the k levels. But otherwise could be arbitrary. Right? So this could also be another, let's say, 2-bit quantizer. Right? So depending on the choice of distribution, the quantizer that you would use would be different. Depending on the choice of the distortion metric, the quantizer that you would design could look very, very different. All right. Right. So typically both in in audio you generally cannot so that's the whole point of lossy compression, or the way you design the distortion metric should be such that you cannot, at least human beings cannot easily perceive the difference between the original signal and the signal that is obtained finally, right? So particularly in audio, there is really no way you can distinguish between the true between true speech, as long as the bit rate is sufficiently high. Uh, it sounds like the exact the original signal itself. But that's also true for images. If you have a higher, after all, every image is a quantized representation uh, of 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 the true image itself. But then if the resolution is sufficiently high, then you can't really see any pixelation. But for example, if you take an image on your computer and then you zoom in, you take a JPEG image and try and zoom in enough, then you can notice pixelation. Right? So you can notice that it looks like different blocks. Right? And that is because you choose the distortion metric well enough. And the distortion metric that you use for, if you use the same one distortion metric for a different application, then then you don't get the same level of quality. Right? So if you use the mean squared error distortion to try to compress speech signals, then it wouldn't sound as good as say an MP3 video, as an MP3 audio file. Okay, any other questions? Synchronization problem if bitrate is high. I don't see why there would be a synchronization problem. So synchronization is typically an issue in, say, communication systems if the clocks are not matched well enough, or are you referring to some other kind of synchronization? That's generally not a problem because if it's an audio signal, then the sound. So are you referring to a communication system?
Yes, in quantization.
Right. So if the bit rate is high, you of course need so so synchronization of let's say, yeah, so let's take the example of voice communication. Uh, if the bit rate is sufficiently high, then uh, then then of course you would need more computations, which could lead to some sort of a lag between the transmitter and the receiver. But again, that's if you have a good enough system, then you cannot really perceive this lag or any sort of a synchronization issue. But you can see it in practice. So for example, if you're using WhatsApp over a poor connection, then certainly there is either a lag. You can there is certain a noticeable lag in certain scenarios, and that is because there is this time offset, right? But this is more so because of the communication system itself rather than the quantization blocks, right? It's because the channel has a lot of errors, and then you either have to retransmit, you have to keep retransmitting certain packets, and that is what causes the additional time offset. All right, any other questions? Okay, so we're nearing the end of the class, so let's have a quiz. I've put up the link in the chat box. Please let me know if you're not able to access it.
Sir, in the first question it is written memory less. So is it non-ID, right?
So it is
So it
IID.
is IID.
It is IID. Okay.
You can maybe take one more minute. Okay, so is there anyone who has not submitted the quiz yet? Okay, yeah, so please submit it. All done? Anyone yet to submit? Yeah, so coming to Anurag's question, would one example of sync issues in the context of compression be compression speeds, where you have two kinds of sources? Such, for example, in MS Teams, the audio, video, and audio are not in sync because of different speeds of compression. Now, most synchronization issues are caused due to uh, due to noisy channels and retransmission itself rather than the the compression. I mean, so compression is partly a reason because the compress. So typically when you have when you're dealing with two different kinds of sources such as video and audio, So let's think about it logically, how one we would do it. We would typically compress the video and audio separately using two different compression algorithms. And you typically have markers. So, so that you know where the video and the audio should align next to each other. Right? And these are sent as two separate streams to the receiver across the network. Now, because if you don't have a good enough network, or let's say that the bit rates are really high, you have you sometimes may need to retransmit certain packets. So, for example, the audio or the video, and these may not be aligned exactly, because otherwise you would have either the video would have to freeze if you wanted to align exactly, or there would be a slight lag because maybe the video was sent maybe some of the video packets needed to be retransmitted, but the audio packets went along just fine. So in these cases, there could be a slight synchronization issue. Uh, but 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 for example, in an application such as say WhatsApp or MS Teams or Google Meet, the the compressors need to naturally adjust the bit rates depending on the network, depending on the conditions of the network. So in this course, we are typically dealing with a fixed compression rate, and you just want to get to entropy or the entropy rate. But in practice, when you are trying to communicate, say, a video or an audio across a system, and this is typically like streaming or so streaming kind of applications where the video or audio needs to be delivered in real time. So in these scenarios, it's if you try to have a large enough bit rate because you want good fidelity, this may not be possible because you have a poor network connection. So in this case, you have to adjust the video and audio quality, or in other words, you have to adjust the rate of compression automatically in order to make sure that the video or audio gets delivered in real time, but at the same but maybe the quality is not so great, right? And sometimes when you try to adjust the rates, there is a slight lag, right? And this could also lead to certain synchronization issues. So these applications are a lot more complicated than what we're dealing with, because you have to adaptively change the rate of compression depending on various other circumstances.
Yeah, thank you. And sir,
Yep.
in quiz,
Uh-huh.
one of the questions the answer was not symbol-wise encoding because of that alpha inside the symbol.
Yeah. So let me just 1 second. Right. So the two questions were the following. The first question is, which of these compression algorithms is universal? It's LZ77 and LZ78. Huffman and Shannon codes are not universal compression algorithms. The other question was, which of these allow you to achieve an asymptotic rate of h of x for a memoryless source? So given an IID sequence xn, and the goal is to achieve an asymptotic rate equal to the asymptotic rate, recall, is expected value of k of xn divided by n, limit n tending to infinity. So both LZ77 and LZ78 let you achieve the entropy rate and therefore equal to the entropy. But for an IID sequence, blockwise encoding using Huffman codes lets you get to the entropy, but symbol-wise encoding does not let you get equal to entropy. So if I do blockwise encoding, then I get a rate of Huffman codes gives me an expected length of n times h of x plus 1. So this divided by n tends to h of x. But if I do symbol-wise encoding, then the expected length is n times h of x. In the worst case, this is n times h of x plus 1, which tends to h of x plus 1 and not h of x.
Okay, yeah, thank you.
Right. Yeah, so block-wise encoding will let you get to entropy, but symbol-wise encoding does not. It's close to entropy, but it's not equal to entropy.
And sir,
Yes.
a universal compression algorithm is something which does not require probability distribution.
Yes. It does not require the probability distribution, and irrespective of what the probability distribution is, it still lets you get, it is still optimal in the sense of minimizing the compression rate.
Okay, thanks.
Any other questions? Okay, so let's end the meeting for today.